All right. So we are going to do a few problems here for chapter 3, some heat problems. And I want you to try to do these before you watch the whole video. So go ahead and pause and try to work out this problem. And then if you get stuck, you can unpause until you get unstuck and then try it again. But being active in the learning process is going to only benefit you. So first, when you're looking at a problem that you think might have to do with heat anything, because it has the word heat capacity, it has energy in it, temperature change, you have two options really. We can use the Q equals MCAP, or we're using the heat of vaporization or fusion, right? Which is really just a change in energy per gram of substance. So the two key things about this, or the key differences here, is that I have a change in temperature. So I can use this equation when I have a change in temperature, and for the heat of vaporization or fusion, that's only during a phase change, and if you remember from those graphs, there's no change in temperature during a phase change. So it really depends on if the problem is prompting us to talk about a phase change or a temperature change. And you may get to where you are in the higher levels and you have both happening, where you're really doing a change in temperature and then you're also doing a phase change where you have to add the energy that you have to do for both of them. We have to add them up. So, or you're doing a phase change and that phase change is giving you energy to change the temperature of something else. So there is a value in knowing how to, navigate these two ways of solving problems. So here, this would be Q is equal to the delta H, which is your enthalpy change, which we'll talk about a little bit later, times the number of particles that you have, or sometimes the mass of the particles that you have. It just depends on the information you're given, right? So sometimes it'll be, an example would be like grams times kilojoules per gram, right? That would give you kilojoules. Or it would be grams times calories per gram or something. It just depends on what units you're given for the heat of vaporization or the heat of fusion, and what units you're given for the mass or amount, N being the amount of a substance. So these are the two kind of main ways we would find Q, which is our heat exchange. So looking at this question, see if you can figure out which way we need to solve this, or do we need to, talk about both of them. So looking at just the kind of the information that I'm given, it's helpful to set up problems where you kind of identify everything. So let's just identify stuff. What do they want us to find? They want us to find the specific heat capacity of copper. So we're going to highlight that. And then they're giving us some other information. So let's just underline some information they're giving us. We're giving you this joules of energy. You have 15 grams of your copper, and you have two temperatures here. So pulling this stuff out is really going to be helpful to super duper be sure that we're doing the right type of math. So what is the variable for specific heat capacity? Notice all the C's in this name, specific heat capacity. So the variable here is C, and I want to know what C is. So C equals question mark. Don't know what it is. That's what I need to find. They tell me about this joules of energy. So this is my Q. It's the amount of heat I'm taking in. Now, maybe you know about energy from some other classes and you want to say, oh, that's E for energy. That's fine, but once we realize we're doing something with heat because they're asking us for the heat capacity, that energy is no longer just a static amount of energy, a contained amount of energy. It is a transfer of energy. So it is really the Q, which is the heat, which is a little bit different than just like stored or potential or even kinetic energy. So we're raising the temperature of this amount of copper. 15 grams is going to be your mass. And then we have two temperatures here, so let's be very explicit about what we're being given. This temperature is my initial temperature, and this temperature is my final temperature. And I know that because they tell me I go from 25 to 60. So I went from initial to final. And you can use T1, T2 if you want to, or TI, TF. And then Sig Fig note, I'm just going to stick a decimal here because I think it should probably be there. It's probably a typo on my part, just so our Sig Figs don't get too wacky. I don't like the ambiguity of that 60, so I'm just going to pretend like there was a decimal there. And if you run across something like this on a test or quiz, just reach out, text me really quick and ask me, do you want me to use the Sig Figs written or should there be a decimal there? Because mistakes are made. So now we can kind of identify all of these things. Notice that I'm kind of pulling them out of the word problem. My goal is to totally get rid of the word problem and that I don't have to use it at all. So over here on the left side, I'm going to just kind of spell out very explicitly everything I have. So I want to know what's C. I'm being given Q, 204.75 joules. I'm being given mass of 15 grams, and I'm being given an initial temperature of 25 degrees C and a final temperature of 60 degrees C. So now I can make this decision. Am I using Q equals MCAT or am I using the heat of vaporization? Because I see a change in temperature, I'm going to use this equation. And so I'm going to pull this equation down into my work area. And you may be thinking this is a lot of writing just for something I can put in the calculator. And I totally get that. But prepping yourself by working on simpler problems in a systematic way will benefit you when you move from simple problems to more complicated problems. And in this class, we're all about building a good foundation. So I know you can probably do this without writing anything down. Some of you can, but I want you to practice the method of problem solving that's going to help you when you can't just look at something and put it in the calculator. So this is more about teaching the process of problem solving and showing your work and communicating your thoughts to yourself and to others, and less about making you do a bunch of work to do some simple math. So identifying what I want specific heat, but right now my equation does not have C equals. And now I know, again, some of you can rearrange this in your head, but I do also know that the biggest mistake I see in a lot of these cases is that students try to plug the numbers in now and they don't rearrange before they start plugging stuff in. So because the C is multiplied by M and delta T, we're going to divide both sides by the things that C is multiplied by to cancel out this work. So we're going to get C is equal to Q over M delta T. Now notice that I have a delta T, I have a change in temperature. So it's helpful to remember delta T is always equal to your final minus initial. You always go to where you're going to get and then look back on where you were and how much you've changed after you've gotten to the end. You can only really tell how much you've changed after you get to the end and look back. So we final first, then we can look back to our initial. So I can really say here delta T is equal to 60 minus 25. I'm going to put that decimal in. And notice that I'm setting this up so that I can really carefully watch my Sig Figs. So the reason why I put the decimal in is so I can use 35. If you didn't have the decimal in, you would want to use 40. That would be more correct, but again, that's not quite as clear. So, okay, so now I have all these numbers and they're so explicitly written out that now I can just plug everything in very neatly. So I'm going to plug everything in. And notice that now, because I did not try to plug the numbers in to this equation, I don't have to go back and forth from calculator to paper and calculator to paper. I can just plug everything in over here, and then I can do all of this math in my calculator at one time, which reduces the amount of rounding I have to do. It reduces the potential for error in going back and forth between my calculator and my paper, and it makes my answer I think quicker to get to and also more accurate. And then, so my final answer, I get a C of, I'll use 2 sig figs 0.39, and then let's take a look at our units. Our units are joules, grams over degree C, and because we didn't cancel anything out, that's going to be our unit for our final answer. So if you didn't get this, I would encourage you to make sure you're putting this in the calculator correctly. It's going to be 204.75 divided by 15 divided by 35. Anything on the bottom gets divided. Do not multiply these together unless you've put them in parentheses, or unless you're using a calculator app like ClassCalc where, you know, it's okay to put things in the bottom because the calculator knows what that means. Your regular calculators, if you put 15 times 35, it's going to bring that 35 up to the top. So if your answer is really too big, that's probably what happened, and you can see me, I can help you out with that, or you can just remember to always put a division sign in front of any number that's on the bottom of a fraction. Okay, so first problem down. Hopefully that was okay. Figured that one out. Good to go. Let's step it up a notch. So let's try this one. Pause and try to work this one out. So this one is a little more advanced, and we're going to go one more, even more advanced. But let's just kind of look and see what we have here. So we have a piece of aluminum. They're giving us the mass, a temperature, and it tells me that it absorbs, which may be important because my Q can be positive or negative based on whether or not I'm gaining or losing energy. So I know that's a positive Q because it's taking in endothermic. What is the final temperature? So that's not quite as easy to find, I think, than some of the rest of these. So we have a specific heat given to us as well. So let's identify some of these things. So they're giving us a mass, which is M, of 100 grams. And they give us a temperature. Now, this is not the change in temperature. This is just a temperature. It is at a temperature of 20 degrees C. It absorbs 1100 joules. That's going to be a positive number because it is absorbing. Now, if it said it lost or emitted, then we would have to put a negative here, and that's really going to help us make sure our answer is correct. So the sign of your Q can be negative. And we can't have negative energy. Because Q is a transfer, it can be negative. It's actually a change. So they want to know, what is the final temperature? And they give me the specific heat, which is C. So what must this other temperature be? Well, if it starts at 20 and then absorbs energy, and I want to know what the temperature is after that absorption, this must be our T1. So now we definitely have a temperature change. So hopefully you're thinking, let's use Q equals M cap. But I'm going to have to break this delta T apart because I don't see the variables that I need. So we're really going to have to break this down. So the algebra here is going to be a little bit more involved, which I can actually get rid of the question now because I've done a good job of mapping out what I'm given. So let's rearrange so that it says TF equals. That's always what we want to do first. And this is really going to sharpen the algebra skills you need to continue on in chemistry. So if I rewrite this, Q equals MC, oops, not delta T, but TF minus TI. I need to isolate the TF minus TI term, which means that I have to divide both sides by MC. Okay, so once I do that, I'm going to get Q over MC is equal to TF minus TI. So now I can isolate this TF term by adding TI to both sides. That will get rid of this term, and I will have TF equal to Q over MC plus TI. And now this looks a little bit weird and a little bit more scary or algebra-wise. You can, if you're feeling like, that's a little much, can I just plug numbers in? In this case, if it gets a little more complicated with algebra, if you're feeling really stuck, I do recommend just kind of plugging some numbers in. That may help you just narrow it down, right? But I do want you to try to brush up on those algebra skills because it's really going to help you not feel quite as behind in your chemistry and science classes as you move forward in STEM. So now that we have terms where everything is equal to what we want, here's where we can start plugging stuff in. So we have our Q of 1100 joules. Watch our units to make sure everything matches up, because my C has very specific units. It has joules, so we have to use joules. If they gave me kilojoules, I'd have to change it. I have grams, and I have grams and delta degrees C, so this is fine. I can use these numbers. I don't have to do any sort of conversions here. 100 grams times 0.90 joules per gram degree C. And we will be canceling some units out this time. Plus my TI 20 degrees. So let's just look at a couple of unit cancelings here. We have our joules on top, grams on the top of the bottom, grams on the bottom of the bottom. And then degree C is going to be up on the top, what we're going to get out, plus degree C. Obviously, we really know our final temperature is probably going to be in degree C, right? So you don't have to do as much unit work here, but it is helpful to know that my joules and my grams do cancel. Otherwise, I probably don't have it set up correctly. So thinking about just getting a number here, I will just do this first part so we can see our Sig Figs, because our Sig Fig rule is going to change. So it's really important to actually work out this in sections. And I want 2 Sig Figs here, so 12. And I don't want to round it yet, so I'll say 12.22. What it is, it's 2 repeating degree C plus, and notice that I'm putting myself in the Sig Fig, my more comfortable addition Sig Fig situation. I get an answer, which is 32.22222, but I've got to cut that off, right? So we're going to cut it off here. So my answer is going to be final temperature of 32.2 degrees C. Now I'm going to ask you this question, which is kind of important in science in general, to ask yourself this question at the end of every problem. Does it make sense? Does it make sense to have a final temperature of 32? If I started with 20 and I added energy, I have 32. Sure. Like, if you got something that was less than 20, it wouldn't make sense, because they're telling you added energy, so your temperature should increase, right? So making sure that the answers make sense is a skill that's definitely important to begin to think about. All right, are you ready for the final level here? Okay, the boss level. So there's a thing that you've experienced called thermal equilibrium. And thermal equilibrium kind of sounds like what it is. It's when 2 bodies that are interacting or touching each other become the same temperature. So I want you to think about your morning cup of coffee. Okay, it's hot. At 9 a.m. it's hot. And then if you were to leave it sitting at 12 p.m., is it still going to be hot? If it's just in a normal mug, it's not going to be hot anymore. Where did that energy go? The energy went out of the coffee cup into the environment. So now your coffee is the same temperature as the room. So now coffee temp is room temp. And if you're like me, you drink it anyway because you need the caffeine, or if you want to heat it up in the microwave again to get it warm. Usually my coffee doesn't last that long, but if it does, I usually don't care because I just need to get it into my body. But this is thermal equilibrium. So you've experienced it. Hot drinks will become colder in room temperature because room temperature is colder. It will become this equilibrium. It will equal the room temperature. If you have a cold drink, like a milkshake, and you leave it in room temperature, Is it going to get colder or is it going to get warmer? It's going to become equal to room temperature, which will be warmer in that case. So you'd have the energy going in the opposite direction. It just depends on what your initial temperature conditions are. So thinking about that mathematically, the heat that was absorbed, in this case, the heat was absorbed by the air and the heat was released by the coffee. They're the same value, the same number, except one of them is being released, so we're going to put a negative sign in front of it. So the same amount of energy that the air picks up is the same amount of energy your coffee is losing, except one is positive because it's being added to the air and the other is negative because it's being lost by the coffee. So just by substituting the fact that we know that Q is equal to MC delta T. I can substitute this Q in and make a new equality. I can say that the MC delta T, the change in temperature times the mass times the specific heat of the substance absorbing the heat, so the air in this case, is equal to the negative mass, specific heat, and temperature change of the released substance, which is the coffee. So now this gives me much more value for an equation because I can measure the mass, measure the specific heat, measure that change in temperature, and really start to isolate some variables and numbers. So what would a problem look like using this concept? Here we go. Determine the final temperature. They will have the same final temperature because thermal equilibrium says they're gonna reach the same temperature. So your TF of your air and of your coffee are gonna be equal, and that's the only way we can solve this because otherwise we have too many variables. When so we're gonna do a new scenario now. We have a piece of iron at a certain temperature and we put it into a pool of water at a certain temperature. The specific heat of iron is 0.450, the specific heat of water is 4.18. And I wanna know what's the final temperature of this combination. So pause and see if you can start. Okay, if you're giving it a try, if not, that's all right. This is definitely a hard one. So let's just draw ourselves a picture to just get a grip on what's going on here. So I'm taking a piece of iron. Okay, so here's my iron. Iron is Fe. And it's hot, okay? So it's heated up. It's 85 degrees. Well, I'm saying it's hot. It's hotter than the water. And we're gonna just drop it right in to this bucket of water. And we're just gonna drop this right in here. So we're just gonna say, hey, this is heated up. The water is 20 degrees Celsius, which is not like incredibly hot. So what are we gonna get? We're gonna get our iron and our water. And let's think about the direction of energy flow. Is the energy, the heat, is the heat gonna be from the water to the iron or the iron to the water? Heat is gonna be from the iron to the water. So we're gonna have a flow out. So the iron is going to experience endo or exothermic behavior. Right, the iron is going to be exothermic because it's losing energy. And the water is going to be endothermic because it's gaining that energy. So here we can say, well, the Q absorbed, who absorbed the energy is the water. It's the Q of water. So we can just kind of replace this absorb, release, and be more specific, okay? Well, the heat absorbed is the heat that the water is experiencing. And then we can say the Q released. So what's releasing the energy is the iron. So let's just substitute all this in. We'll say the Q of water is equal to the negative Q of the iron. If you're having issues or you're like, I'm really lost, text me right now. Or you can absolutely come to office hours to get help with this, but definitely text me if you're, send me a picture of what you're watching right now and get some help. Okay, which means that we can substitute even farther and we could say, well, the MC delta T of water is equal to the negative MC delta T of the iron. And now here's where we get to where got information, right? We can start plugging some stuff in. But first, because they're asking me for the final temperature, I don't see final temperature in my math, right? I just see change in temperature. So I really need to isolate the two temperatures out. So I need to kind of break this down a little bit more. So let's break it down. I'm going to make it kind of big here because it's going to be what we're using for the most part. And we're going to say, put brackets, TF minus TI, and all of this is of water. So I can't put the mass of the iron here. So just being very clear with myself, all of that has to be about water. MC and then TF minus TI. And I'm going to say something very weird for you to hear coming out of my mouth, but I do not want you to rearrange the variables for this. You totally can if you're like super flexing your algebra skills. But for this complicated equation, it is actually easier to just put your numbers in first because it is much more complicated to try to rearrange the variables, all right? Because most of these things are going to cancel out. My MCs are going to multiply together and I can distribute them. It's just easier to plug numbers in at this point for this type of math. So it's just a little more complicated than the previous problems. And I would say that unless you're really trying to flex some super algebra muscles, it's probably faster and easier to understand if we just try to plug something in at this point. So let's do that. Let's just plug some stuff in. So let me color code a little bit for you. So I'm going to do everything about iron in orange, and I'll do everything about water in purple. Okay. Just to make sure we're all good here. So over on the left side, I'm talking about water, so I'm going to use all my purple stuff. I've got my mass, 75 grams, and I'm going to set this up with units, and then I'm going to get rid of my units. I know, and you're like, who are you? I know, but because it just gets so cumbersome, and as long as I check and double check that I've written everything down correctly, my units should work out, and I know that final temperature has got to be in Celsius, right? So my initial temperature of water is 20.0. Okay, so this is all for water. And then my iron stuff. And notice that I put TF in both places because I know TF is the same for both. Okay, sorry that I kind of cut that off, but we'll fix it later. All right, so now I kind of have everything set up. I know where my numbers are going to be, and I'm going to just get rid of those units, y'all, because I can really see here how it's going to work, right? I can see grams are going to cancel, joules are going to cancel because I'm going to bring joules over from one side to the other side and divide them eventually, so they're going to cancel out. And then my degrees C are obviously going to cancel here, but they're going to be left in one side for the final C. So if really you want to lose your units at this point, it is a lot easier to visualize all the things that need to happen if you do lose your units. And I won't say that about anything else ever again. But this problem is a little bit easier to do so. So we also got to be really careful about our Sig Figs. So we got a lot of multiplication, division, and we got some addition, subtraction. So we're going to track those Sig Figs as we go. Okay, so if you want to give this a shot first, to just kind of break it through. The rest is just algebra. The chemistry is over with. The chemistry stopped when we set this up. That's chemistry. The rest is math. So I'm going to take you through the math, but I want you to definitely try it before we go through it. Okay, so I'm going to get my calculator out, and we're just going to start by combining some like terms. So I'm going to try to just isolate this TF because the TF is the same on both sides, and that's also part of the chemistry, right? So we use math to help us figure out science. And I'm going to go step by step. I'm just going to multiply some of these things together just to get some terms that just simplify. Just simplify. And I'm keeping all my numbers, all my zeros, all my Sig Figs, okay? So do a quick Sig Figs check every time you finish a step. I have 3 sig figs and 3 sig figs. I need 3 sig figs. So that 5 is going to stay. This 5 here is going to stay for rounding. And also going to stay because 313 is different than 3,135. I can't really lose that place. I'm going to keep that around because I'm not wanting to round quite yet. But I do need to remember that this is actually just 3 sig figs. And then here I have, on the other side, I have 3 sig figs, 3 sig figs, and 3 sig figs. But I'm going to keep, again, this 5 around because I don't want to round yet, but I do want to underline that I'm only talking about sig figs here. So I'm going to underline my sig figs in blue because it's going to help us to keep everything straight. So now let's distribute. I know I'm no Sal Khan with math, but I hope that this makes some sense. I'm not a math teacher. I don't claim to be a math teacher at all. But I can show you. I have a hard time explaining why something is, but I can definitely show it. Okay, so we have 11.25 times 85. A negative times a negative is positive. Okay, so let's pause and do some sig fig work. And I know that some of you are like, oh, but I have to do sig figs, it takes forever. Trust me, tracking it through is a lot easier than going back and trying to figure it out. So I know my sig figs from this numbers right at the same. Now I take 3 sig figs and I multiply it by 3 sig figs. This is not 4 sig figs, only 3 because of the step previously. So 3 times 3 with 3 is going to be 3. Over here I have 3 with 3, also going to be 3. I'm not going to round these yet. We're not done. So now we're going to combine like terms. I want all my TFs on the same side, and I want all my non-TF terms on the same side. So I'm going to add the 11.25 because I do not like dealing with negative numbers. So I'm just going to add, the 11.25. And notice that I'm going to set this up for sig fig work. And then we're going to add the non-sig fig term, or the non-TF term, sorry, to both sides. 6, 2, that is not going to be enough space, huh? So this needs to be 0, 0, 7, 2, 6. We're adding that. So this will cancel, these TF terms, and this will cancel. So now we can really look at what's going on with sig figs, just these two areas. So I'm going to have 0.25 TF. I'm just doing my math out by hand. It's pretty easy for this one. Of course, on a test or exam, you don't want to trust your calculator. You want to trust your brain and use your calculator for sure. I've definitely made little mistakes before. So looking at sig figs, okay, the 11.25 was the 11 and the 2, and the 627 was the 627. Okay, so looking at my sig fig places, I'm going to have to cut off this number here, okay? And I'm going to have to cut off this number here. So that doesn't mean I have 314 and 636. I cannot round these numbers again. So we're not rounding, we're just kind of keeping, use blue here. Well, let's use orange for the addition subtraction rule and blue for the multiplication division rule. Okay, so let's just kind of bring all this down into a nice, neat area. Equals 63656.25. And then remembering from our addition subtraction rule, still got these sig figs, and not the whole number gets to be used. So dividing both sides to make TF by itself now for our final step. When something cancels, we really don't have to look at it as sig figs anymore, but we do want to look at it as sig figs on this side. So I'm going to get a final answer here. Finally, that I'm not going to round anything. So we're going to get TF equals 20.2324195. Okay, now we're definitely going to round some of this. So I had 3 sig figs divided by 3 sig figs. We're going to get 3 sig figs in our answer. So when we do our sig fig rounding, 20.2, and then we know this should be degrees C. So here's my answer. I use approximation when I round for sig figs, but you can just use a regular equal sign as well, it doesn't matter. Beautiful, isn't that fun? So that's kind of the hardest thing I can ask you about this heat stuff and this heat math. So definitely go back and, you know, maybe retry this problem on your own if you had some struggles with it, and make sure you're getting that same answer, and you have now the work you can look over to see where you got it wrong.